Yes, welcome everybody. I'm excited to introduce this session brought to you so with two speakers from NVIDIA, so two of the people right at the heart of NVIDIA's efforts on climate research. So we have Alison Lowndes, who's a senior scientist, global AI at NVIDIA, has been working in this space for more than 6 years now and helped found the NASA Frontier Development Lab, which I think you're gonna hear a little bit more about during her talk. And David Lowndes, David Hall, who is a data scientist at NVIDIA, working on, as I say, climate research and also questions of using AI to improve science more generally. So I think David was having a little bit of technical problems, but I think he's back now. So if he's ready, I will hand over to David and let you have the floor.
Hello, can you hear me?
Hi, David. Yes, we can hear you loud and clear.
Yeah, I'm rebooting my computer. My computer is having technical problems. My phone is functional.
Okay, no problem.
I apologize for the delay. Hopefully it'll work itself out soon.
This happens to the best of us, even those in IT, I guess. So no problem.
David, do you want me to share your first few slides?
Please do until I get things sorted out on my side.
Okay, bear with me a second. I know you updated them, so I'm making sure they're more recent edition. Bear with me. Hopefully you can see that.
I can.
That looks good.
So just tell me when to flip forward, David.
Yeah, I'm almost functional. So one moment, I should be able to join from my computer. Sorry, I don't know what happened with my machine today.
It's a good job it wasn't Zoom that went down yesterday. I'm not sure what the world would have done. I think we can probably live without Facebook.
Strange day for my computer to die. I'll try one more time, then we'll have to do it over the phone, I suppose.
You could always just run it local there and tell me to change the slide.
Yeah.
You come across very well over the phone, David. So we could probably with the slides until your computer works again.
Yeah.
Okay, wait, I think I'm there. Come on. You can do it, computer. Be my friend. Okay, can you see me?
Yes.
Excellent. I am now connected to my computer. I will share my own screen just to make it easier.
All right, I think I'm ready to go.
Brilliant. Over to you. Thank you, David.
Thank you. Hello, and thank you. Now my sound is driving me crazy. Can you hear me still?
Yes.
Excellent. All right, hello, and thank you for inviting us to speak as part of this fascinating AI for Good virtual event. I'm David Hall, a senior data scientist at NVIDIA, and I'll be presenting the first half of our talk focusing specifically on climate change and some of the ways NVIDIA can help tackle this challenge. Then in the second half of our presentation, Alison Lowndes will give us a better, broader perspective on this topic. It's clear to me that climate change is one of the most important and pressing problems of our time. And in my opinion, the plan put forth by EU's Project Destiny provides one of the clearest visions of how NVIDIA can help tackle that challenge by building detailed, interactive, and powerful digital twins of the Earth. Together with the help of our collaborative partners, NVIDIA is uniquely suited to making that vision a reality. While the importance of global warming isn't new, it's clear that something recently has changed. Our estimation of the severity and immediacy of this threat has been shaken by recent events. Over the last several years, frequent weather disasters across the globe have demonstrated that dangerous impacts have arrived. There have been fires, floods, heat waves, droughts, mudslides, and tropical cyclones, with a frequency and severity never seen before. They've occurred in every country at every latitude in both hemispheres. No nation and no region of the globe is immune, and the damage that's occurring appears to be far greater than our best models to date had predicted. The cause of this problem is no mystery. We know that climate change is caused by greenhouse gas emissions, primarily from our extraction and burning of fossil fuels like coal, oil, and natural gas, but also from livestock production, agricultural waste, transportation, cement and steel production, heating and cooling, and widespread land use and deforestation change. We also know the solution. Combating climate change is primarily an act of political will. Governments across the globe need to choose to enact legislation to reduce and eventually ban the use of fossil fuels. In its place, we need massive expansion of renewable energy sources. We need to incentivize sustainable technologies, and we need massive infrastructure projects to modernize transportation, agriculture, and manufacturing, and to adapt our cities to be more resilient to disasters. These efforts will raise costs, so income assistance will probably be required to offset them. And since we all live on the same planet, wealthy nations are going to need to assist poorer nations to help develop their energy resources responsibly and to avoid further deforestation and wetland loss. If history is any guide, governments are unlikely to act until the disasters have become so frequent and so expensive, it's clear that we cannot afford not to act. Unfortunately, at that point, much of our funding will go into rebuilding and recovery rather than prevention. In the chart shown here on the screen, you can see the rapidly rising number of billion-dollar disasters in the United States in recent years. We now have 20 per year instead of just 3 or 4. In any case, once governments do decide to act, we'll find ourselves in a race against time. It'll take multiple decades to transform our technological systems, and the global temperature will be rising the entire time. And with each degree of additional warming, the number of disasters will increase exponentially. We also risk hitting dangerous tipping points, both known and unknown, which could dramatically accelerate the rate of change. Once action is mandated, it's ultimately industry and academia that will need to make this transformation happen. Collectively, we will design and build the solar power plants, carbon capture facilities, ocean desalination plants, and smart cities. But how are such things accomplished? Through an iterative process of modeling, production, and improvement. By doing as much of this as possible in simulated environments using digital twins, we can speed up the process and minimize the costs. Modeling and simulation will play a critical role in every activity designed to fight climate change. Models are needed to predict the impacts of climate change. They can accelerate the design of new sustainable technologies and the discovery of new materials for energy storage and transportation. We can use simulations to optimize complex systems and to provide intelligent feedback and control. Observations will also play a major role. The Earth is surrounded by a high-quality satellite and sensor network that can provide detailed feedback on current conditions. With these observations, we can detect and track wildfires, tropical storms, and other natural disasters. We can improve search and rescue and detect harmful greenhouse gas emissions. Observations are also critical in data assimilation for weather forecasting. We're beginning to see some movement towards large-scale climate action. For example, the EU and UK have enacted legislation designed to achieve carbon neutrality by the year 2050. Part of that effort includes a large-scale modeling initiative called Destination Earth. Its goal is to design digital twins of the planet that we can use to understand and combat climate change. Destination Earth is just one of several important climate modeling initiatives. For example, the AI2 climate model is dedicated to accelerating climate science by better exploiting the world's fastest supercomputers using modern programming languages, machine learning, and open source collaboration. CLIMA, the Climate Modeling Alliance, expresses similar goals. The brand new NSF initiative, LEAP, is focused on AI techniques in particular. Project Destiny provides an appealing vision of what the future of Earth system modeling could become over the next decade. It describes intuitive user interfaces, responsive answers to what-if questions posed by decision makers, high-resolution storm-resolving models, unified open access to satellite observations, and energy-efficient exascale computing. While Destiny provides a highly ambitious vision, it just so happens that NVIDIA's technologies are perfectly suited to making this vision a reality. For example, NVIDIA's Omniverse can provide the real-time interactive experience needed to make digital twins intuitive. To make it responsive and fast, we can build AI emulations or surrogate models of the world's top weather and climate models. Physics-based models, now referred to as Earth engines, will be as important as ever. And with the help of NVIDIA's new Grace CPU, we can train these models in record time. All of this can be powered by NVIDIA's superpods, which are some of the most capable and energy-efficient systems on the planet. Destiny envisions digital twins that are as intuitive and simple to use as any app on your tablet. Omniverse can make this happen. It can provide real-time ray-traced environments that enable you to interact with a digital twin as if it were the real thing. It can also operate as a central nexus for standardized access to models, data, and observations. The video on the right, which is not currently playing, there we go. No. The video on the right shows a sample of weather model data rendered in Omniverse. An important goal of Digital Twin Earth is to explore the impacts of a given decision. For example, you might ask which regions of your country will experience increased flooding under a given emissions scenario. Today, answering such a question might take weeks. However, it's possible to generate near real-time results through data-driven models and emulations. This was first demonstrated by the WeatherBench project, which trained a ResNet model to produce near instantaneous medium-range weather forecasts. NVIDIA enables this layer by providing a full-stack solution for training AI models. In Destination Earth terminology, physics-based models are called Earth engines, and they will be as important as ever, as they are the only sure way to generate accurate physical predictions of climate conditions that haven't yet occurred. In fact, these models will need to be pushed beyond their current limits to hyperscale resolutions of 1 kilometer or higher in order to fully resolve storms without convective parameterizations. Additionally, we can build digital twins to model other important subsystems of the planet, like forest fires, floods, power grids, as well as biological, social, and economic subsystems. Enormous AI projects and GPU-accelerated HPC models have traditionally been limited by the bandwidth between the GPU and the CPU. NVIDIA's new ARM-based CPU called Grace overcomes this limitation by tightly coupling the two together. This gives 30 times the bandwidth and 10 times the performance when training giant AI and HPC models. Grace is a major breakthrough in the types of models we'll be able to build and train. In order to simulate how the Earth's climate will change over long timescales, models are typically run at a coarse resolution, as shown on the left. This allows them to capture large-scale climatic patterns and trends, but they can't predict future weather extremes. Nor can they accurately model some very important cloud processes, leading to uncertainty. Building a cloud resolving model at 1 kilometer resolution would be sort of the holy grail, which would solve both problems. Getting there would require a performance increase of 10 million times relative to today's present 1 degree simulations. On machines like Alps, the raw computing power of NVIDIA's GPUs together with the Gray CPU should enable us to achieve about 10 kilometer resolution globally for climate simulations. And the generation of supercomputers after that could finally close the gap. Once fast data-driven digital twins have been trained, they can be coupled together, which opens up a whole new realm of possibilities for exploring complex systems interactions. And this is precisely what's needed to answer those what-if questions posed by decision makers. For example, a climate emulation could provide initial conditions for a weather emulation, which could then provide wind and cloud predictions for power plant models, which in turn could be used to optimize our electric grid. When models are fast enough, both one-way and two-way coupling are possible. One can imagine going a step further. Instead of a user manually testing one configuration at a time, we could employ reinforcement learning to optimize our system, given a set of financial, legal, and social constraints. For example, one could launch an automated search for the best possible placement of a seawall, the best distribution of wind and solar power plants, or the optimal transportation system. NVIDIA technologies can help in the operational phase as well. After these systems have been designed and deployed, NVIDIA's Jets and Edge devices can provide the intelligent feedback, control, and coordination necessary to ensure their safe and efficient operation. Let's look a bit closer at how this Omniverse model might work. Omniverse Nucleus Server can act as a central nexus for exchanging information between a multitude of models, data, and services. A user might interact with an Omniverse-based application, like Omniverse View, as shown on the left, or their favorite existing tool, such as Kitware's ParaView, shown on the right. Through Nucleus, you can access and interact with large remote data and models without having to move that data or model onto your machine. Each of the green arrows in the center picture represents a connector. It's a small piece of code, like a plugin, that enables a given service to communicate with Omniverse. Omniverse is not intended to replace your existing tools, rather it provides a common platform to unify and simplify the discrete components of your scientific workflow. Although it's most obvious how NVIDIA's technologies can contribute to climate and weather modeling, the same basic principles can be applied to each of the important climate-focused areas listed here, including climate mitigation, adaptation, monitoring, as well as disaster response, climate justice, and geoengineering. In this section, I'd like to review some of our ongoing research collaborations to show how they fit into this larger vision. NVIDIA is working with industry and academic partners across the globe. The number of collaborations is really quite vast. Since I don't have time to discuss them all, I'm just going to focus on a handful of the projects in which I'm personally involved. In Europe, I'm working closely with our industry partner, ATOS, as well as major climate and weather centers such as ECMWF and DKRZ. In the US, I'm engaged in projects with major climate and weather centers, including NOAA, NCAR, NASA, and Oak Ridge National Lab, as well as the NSF Institute called AI2ES. In my opinion, one of our most exciting projects is our new effort investigating full model emulation. In collaboration with ATOS, we're working to construct AI replicas of global weather and climate models based upon the WeatherBench dataset from Raspidal, and the related work by Dale Duran's group at the University of Washington. Once trained, we estimate that a 10-day forecast at 10-kilometer resolution could be produced in as little as 13 seconds on a single GPU. This is in contrast with operational weather models that take roughly an hour on 100,000 CPUs. This represents a potential speed up of about 30 million times. Currently, however, an emulation at 10 kilometers remains theoretical, as there are significant technical hurdles that need to be overcome to build a model of this size. But that's exactly what we're working on. What's the advantage of an instantaneous forecast? Well, weather is chaotic. Using physics-based simulations, we can only afford to simulate a handful of ensemble members. This sample is likely to miss many rare but highly impactful extreme weather events that might occur. Instantaneous forecasts enable us to explore thousands of ensemble members, more accurately detecting and quantifying the risks. At present, the highest resolution achieved in full-scale emulation has been about a degree, due in part to the limited quantities of training data available. But can we push past this limit? With enough resources and innovation, I believe that we can. Potential avenues of advancement I'm excited to explore include transfer learning, physics-informed neural networks, active learning to generate data on demand, transformer-based models for scalability, and generative models for producing more accurate atmospheric states. Increasing the resolution of a physics-based model takes many years of work. In contrast, building a more sophisticated data-driven model is simply a matter of compute resources and scalability, as demonstrated by the amazing GPT-3 language model, which is just enormous. Physics-informed neural networks can greatly reduce the amount of data we need by adding physical constraints back into the system. This can provide the best of both worlds. Nvidia Simnet is a tool for implementing physics-informed neural nets for multi-physics simulations. It's not currently set up for climate and weather simulations, but in principle, it could be adapted for that purpose. Each member in an ensemble forecast needs to be analyzed to detect and track extreme weather events. In collaboration with ECMWF and NOAA, we're working to move automated tropical cyclone detection from research to operations. AI detection of cyclones will be faster, more accurate, and more robust than existing heuristic techniques. When combined with a large ensemble, we can provide a far better statistical assessment of the likely track and behavior of these dangerous storms. We can use similar techniques to monitor storms on the surface of the sun. In an effort to predict impactful space weather, working with the heliophysics group at NASA Goddard in Altamira, we trained neural networks to detect features using data from the Solar Dynamics Observatory, which were able to track and automatically label sunspots, active regions, and coronal holes with a high degree of accuracy. NVIDIA's in-painting technique uses partial convolutions to repair damaged images. Researchers at DKRZ, NVIDIA, and UF Berlin realized that this same technique could be used to fill in missing climate observations as well. We used transfer learning from reanalysis datasets and fine-tuned it on the HADCRUT-4 climate observation data. This model was able to accurately reconstruct global gridded observations as far back as the year 1850, giving us a more accurate estimate of global temperature change over time. This work was published in Nature Geoscience and was included as part of the recent IPCC AR6 assessment. Together with ECMWF and ATOS, we're working to improve weather forecast data assimilation by removing persistent patterns of temperature bias. Employing satellite occultation, more accurate atmospheric temperatures can be determined after the fact. Using this as a ground truth signal, we've trained neural networks to remove this bias. NVIDIA's collaboration with NOAA is very active. We support their Hera supercomputer and help organize AI workshops. Perhaps most importantly, we run a series of hackathons where we provide dedicated assistance to NOAA researchers looking to improve their AI and HPC codes. We also support individual research projects across NOAA. Our most active collaboration has been with their Global Systems Lab. This team works on a wide variety of research topics, including AI-based cyclone and convection detection, as well as improved fire, radiative transfer, and soil moisture modeling. Another important organization NVIDIA supports is AI2ES, the NSF AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography. This large NSF-funded team focuses on trustworthy and explainable AI methods for the environmental sciences. One of their major goals is to increase meteorologists' competence in AI methods in order to help them move from the research phase into active operations. The last project I'll mention is a modeling collaboration with Matthew Norman and Murali Meena at the Oak Ridge National Laboratory, where we trained neural networks to learn subgrid scale turbulent dynamics. This new physics parameterization enables a coarse CFD simulation to reconstruct subgrid scale eddies. As you can see, with the aid of a ResNet model, we were able to accurately predict the fine-grained turbulent structures produced in a high-resolution large eddy simulation. So to summarize the first half of our talk, climate change is upon us and we have a limited time to act. NVIDIA is interested in doing what it can to help. We like the ambitious visions of forward-looking projects like Destiny, AI2, Klima, and Leap. We think we have all the pieces, both hardware and software, to make such a vision a reality. I personally plan to focus much of my attention on important challenges in this area in the next couple of years. If you have any questions for me, feel free to contact me at dhall@nvidia.com. Now, I guess it's time to hand over control to Alison, who will provide us with a broader view of this topic. And thank you for your patience with me showing up late. My apologies.
Thanks, David. While I'm switching over, do you want to go to just click the Q&A at the bottom? There's a question there while I'm moving screens over.
Is it possible to simulate environmental pollution, such as plastic polluting water bodies, creating a digital twin to assess the impact of recycling in the affected region? Interesting. I mean, I don't actually know the answer to this question. You can create digital twins of many different systems. If you have a model of the recycling process and the pollution process, I guess you could do a tracer transport for figuring out where the pollution is going to go. So yeah, I mean, the water body problem is not too hard. Actually, tracking the sources of pollution is something a little bit outside of my realm of experience, but yes, I believe it's a doable thing.
Thanks, David. Okay, so moving swiftly on, I'm assuming that we're good for time here. So David's given you a glimpse of just some of the work that NVIDIA does in this field. 20 years ago, we were actually all about graphics and visual computing in gaming. And we're very proud of our roots because gaming itself, I believe, is still something like 60% of our revenue. And it's actually now a very, very integral part of what is and what has to be successful deployed artificial intelligence. And hopefully I can show you why today. I personally operate in our public sector division now, although I'm typically off Earth applications, so space-based. You know, my head has always been in the stars, but as well as the terrestrial work that we actually do. I'm an ex-solutions architect, and I now work on all these kinds of applications, ranging from geospatial to robotic autonomy on the moon, to artificially intelligent satellites, and even linking the moon's 4G network. It was chosen because 4G is very established and stable, but linking that to our terrestrial 5 and 6G networks. And of course, all of this tech is continually evolving at a far faster pace than humanity can adapt. So every day really truly is fascinating. But I also advise on and help implement our climate action framework, note action. And this is mitigation, so reducing emissions, adaptation, so preparing for the consequences, monitoring via Earth observation satellites, and ultimately altering or at least nudging population scale behavior. You know, ultimately that's the key to this. But this, of course, includes advising on NVIDIA GPUs, so that's graphics processing units, and today's modern accelerated form of computing. David told you about Grace, our new CPU, but the only way that we will compute cloud resolving high resolution weather and make the climate predictions that we need to push people to act is with accelerated computing. And we were actually just pipped at the post by Japan's MN3 system from Preferred Networks, which is now the world's most efficient form of compute. And although we missed, I think it was something like half a gigaflop per watt, our actual hardware, our accelerated hardware and platform features in number 2 to number 15 of the world's most efficient. So this is getting the most compute for the smallest footprint. as Sarah was asking about this earlier in chat. Each of these gold boxes that you can see in this image saves 300 tons of CO2 a year. And in our data center alone in Santa Clara in California, that's 168,000 tons a year saved simply by using DGX as opposed to CPU's traditional architectures. But also because we can exploit something called parallel programming. You know, we can do trillions of mathematical operations per second simultaneously. And that figure in the left there of 2.8 exaflops means that we're actually capable with this system, with this data center, we're capable of computing 2.8 quintillion, that's 10 to the 18 floating point operations per second, whilst being almost now the world's most efficient compute on the planet. Preferred networks actually beat us, as I said, by I believe 0.45 gigaflops per watt. But as you know, people like to compete. This is a very competitive arena, so we're only going to gain more and more efficiency as the months go by. So my team's ultimate goal is to spread that message and to upgrade more and more nations to use the most efficient for harnessing AI across the many different applications. And this is also why we have our Turing GPUs on board the International Space Station. This is with HP's Spaceborne, their second gen. Data centers in space will actually take a little longer to establish, but all major CSPs, so that's cloud service providers, are now ready for direct satellite downlink. So AWS has ground station. I think they have at least 10 of these data centers now, specifically for satellite data. Microsoft Azure actually have a link direct from the ISS itself and are currently testing. We also have many partners who ruggedize our embedded small factor low swap, so swap is size, weight and power GPUs, and you know they can be credit card sized in an embedded ruggedized form. And this is the latest from AI Tech that was originally founded in Israel but now operates across the US and worldwide too. The space startup ecosystem is actually booming. Billions are actually being invested, and another partner, Orbital Sidekick, have had our Jetson range of embedded GPUs in orbit, offering something called hyperspectral imaging since 2018. And there are many of the major satellite operators that are now deploying low-cost GPU-based CubeSats to actually increase the mesh coverage of the planet, you know, with their existing constellations. And I also work very closely with the European Space Agency. They commissioned this study quite a few years ago now with the Barcelona Supercomputing Centre as prime and Airbus. And they're currently testing our latest hardware, but already show that GPUs have impressive performance for short-term missions, and that's rad tolerant as opposed to rad hard. Unfortunately, although there's another 3 years of the commission left, we keep innovating and at a very, very fast pace. So basically, as soon as they finish testing one, we've brought out another that's even better. So it's a great problem to have. But ESA then enables the entire ecosystem of enterprise, startups, etc., right across Europe, who are actually, you know, these are the folks that are addressing the hundreds of different types of use cases or applications for satellite data. And one huge, as yet nascent market is actually satellites and OTA, so over-the-air updates. Starlink and Tesla will actually be the first to harness this. Although their receivers are currently, they're not small enough for cars, but they are for their truck fleet, their autonomous truck fleet. But this is the only way to exchange the vast quantities of information that's needed by self-driving vehicles, and the only way we can achieve connected vehicles, the safest form of autonomy. So Vehicles themselves can generate terabytes of data an hour from cameras, radar, other sensors, and must pull in massive amounts more to navigate. And they currently do that sharing our own cell towers. So this has to evolve. In fact, car makers are they aren't now betting on selling cars as much as they will be selling owners a continuous stream of OTA, over-the-air services. You know, think of like how we operate iPhones and mobile phones today with apps. But most of the actual satellite operators are currently, you know, and have been for many years, beaming data down to the airline industry, to the military, to the marine industry for shipping routes, etc. And we have something called Aerial, which is an offering that can actually reduce the time it takes for signals to travel from space to car. So let me know if you're interested in that. But what about the actual research? You know, surely that needs to be accelerated too. So, you know, time sure flies. I actually first joined NVIDIA just over 6 years ago now, can't believe it. And one of the first things that I did was help to establish the Frontier Development Laboratory, FDL, which is itself a research accelerator that applies AI to space science. It's pushing the frontiers and developing new tools very quickly over a summer, over an 8-week program that then gets fine-tuned for the rest of the year. But this is to help solve some of humanity's biggest challenges. You know, we cover all manner from detecting potentially hazardous asteroids, to twinning coastlines, to model flood risk, to predicting solar flares that could knock out national and international electricity grids. This slide is actually a year old now. We have FDL, Australia and New Zealand, that actually started in 2022. And this is an example of some of last summer's work that was just published in Nature. So applying Horus to raw images takes less than a minute using GPUs. And that means it could very easily be deployed at scale, and will be. This is work with NASA that will actually aid decision-making for our permanent lunar base. So the base that's going to start getting built on the moon. And this is actually one of the moon's South Pole craters that is actually illuminated by ray tracing, which is the GPU's inherent ability to literally retrace paths of light. Most craters on the moon are permanently in shadow, but now we can use GPUs to provide essentially night vision. And this again is work with NASA for their Viper lunar rover mission, and even onboard AI. So having smart satellites now, as well as simply ground-based, you know, using larger data centers and running AI on the ground when you downlink to the actual data for enhancement of imagery, something called super resolution. And this is again work for NASA's Viper mission, which will be landing a rover on the moon in 2023. Next year, FDL Australia and New Zealand will again resume the work of applying AI to oceanic carbon sequestration and also marine restoration. So look out for blue carbon, and University of Oxford with Ocean Mind. This is, I'll actually provide a copy of these slides for you. They've actually been sent, so hopefully they'll be distributed shortly for you to look at these in much more detail. But this is just some of the many outputs from FDL. All code is open source, and much of the work is actually already deployed. This year, we also expanded to digitally twinning coastlines after the team here provided 3-day warning for extreme rainfall. So being able to predict rainfall before it wrecks harvests and takes people's livelihoods away. And David talked a lot about those processes used earlier. But we can actually couple this with work that we've been doing on a type of simulation and modeling that we've actually been developing for many, many years. So it's actually now really, really simple to actually pull in different capabilities in order to solve these problems. When you look at this, hopefully you can see where gaming has already given us the technology to contribute to these kind of solutions. This is physically accurate modeling. And it originally had to be because gamers wouldn't accept anything that wasn't accurate and looked like real life. But now it can be similarly used for actual physical modeling. This is work by my colleague Stefan Jeschke and et al. And colleagues. I also work with JPL. This is actually a very old image of their Mars Athena testbed, which runs on our GPUs. And most of the winning teams of what's called, you've probably heard of DARPA, but DARPA has a subterranean challenge that's been ongoing for a few years now. And most of the winning teams also use our GPUs. This is R&D, research and development for autonomous rovers on Mars to actually search through lava tubes for appropriate sites for permanent habitats, that aren't really high in radiation. Of course, they also help us here on Earth in dangerous, dark and dirty places, such as in nuclear decommissioning. And JPL also have our DEX pilot code from our robotics lab here in Seattle. This teleoperation system uses something called Riemannian motion policies to generate really smooth actions. And so think about controlling a surgical robot remotely here on Earth, or even a robot on the moon. So originally, we were talking about the gaming side and how this links now with artificial intelligence. We have a term that we've been using for quite a number of years now called metaverse. This is a general term that actually describes quite a number of different concepts. David's already told you about digital twins of Earth, and this is actually just a natural extension of what we've been doing for decades with physically accurate gaming. But it's also the most efficient, cost-effective and risk-free way of prototyping everything from cars to building. Architecturally, we designed our build 2 new buildings in Santa Clara, Endeavour and Voyager, using these technologies. Prototyping robotics and robots in car manufacturing plants, in power plants. The metaverse is basically like a 3D internet. So they're virtually extended physical spaces. In fact, we already exist in both physical and virtual worlds. Here now, we're together virtually. In fact, society wouldn't have been able to continue operating throughout COVID without Zoom and Teams and web conference, for example. But over the past few years, we've actually been developing what we call Omniverses, as David alluded to earlier, to actually connect these worlds. And more on that in just a moment. But this code, for example, visualizes the AI technique of generative adversarial networks, or GANs. These are 2 competing neural networks that learn together. And using GANs, you can actually teach a neural network to fill in gaps or missing data based on prior knowledge. Here, they're turning rough doodles into photorealistic images. And the interactive app that we christened GoGAN after the Impressionist is actually available online. You can just search it using Google. And the resulting images are what we call synthetic images, albeit convincing imitations. And the incredible thing about virtual worlds is they're infinite. They're actually bounded by your graphics capability and the memory that you actually have in your computer system. But here we have a robot learning to navigate on its own with a technique called reinforcement learning. But they can train in parallel. So hundreds of different agents all trying to be the best that they can be, essentially. Here, it's easy to see the capabilities of working in virtual worlds at no cost. Each iteration, each room has slightly different parameters, something called domain randomization. So here you're also generating masses of synthetic data all the time. As for the agents, the first to reach its goal wins. This is actually work with ETH Zurich, the RSL Robotics Systems Lab in Zurich. So domain randomization is actually, I'll just kick that off, is very important to be able to cover all of the corner cases, the unknown unknowns, to train an AI system to cope with unexpected scenarios. And here we show simply different lighting, something that's very simple to do. Think gaming, when you lose a life, you just start again. There's no actual loss there's no loss of life, there's no loss of money, just nanoseconds. So it's very easy to generate data as you're actually using virtual worlds. And once you can generate synthetic data, it's no big step to generate entire synthetic worlds. And we're working on this now, particularly for our autonomous vehicles, autonomous cars and robotics. A world or even a city is far too big to actually fit in memory entirely. So what you do is you simply split it into blocks or tiles, but seamlessly assembling the necks as you drive, or the robot moves, or as we zoom into a globe for a digital twin of Earth, similar to how we will actually think Google Earth and how you can zoom in and zoom out to get much more data. It's not until you zoom in that you actually get that data. Something called foveation. Let me just turn that volume down. Foveation describes how our eyes actually blur out the peripheral. We can see motion but not detail on the outer edges. And as you can see here, look towards the outer edges. This is how a computer generates a point cloud, of the upcoming area. And we only have to generate the actual digital virtual version of it as we get closer to it. It's a very similar concept with our eyes and brains. But most development today is in autonomous vehicles because the market is huge, but also because it's a highly complex problem. And if we can solve it, we can solve the rest. AI is really mathematics wrapped up in code, and mathematically, it's all the same whether you're talking about driving along the coast of San Francisco or Jezero Crater on Mars, where the Ingenuity drone is actually still operating. And when you combine that with modeling and visualization, you can see how creating a virtual world is actually child's play. Here is an entire galaxy, essentially a digital twin, in fact, a fully interactive twin to study the outflow from supernova. It's a simulation, a physically accurate model of an entire galaxy, although the full astrophysical sim itself requires a large cluster of at least 10 DGX systems, and there are 8 GPUs in each of those, and something called Chola, which is a GPU accelerated code library that was written by Evan and her supervisor Brant at Pittsburgh and UCSC. This animation sequence alone is over 3.2 terabytes of volumetric data, but it can be done. So Omniverse, as David alluded to earlier, is open to all, and we're actually only just scratching the surface of combining it with natural language processing, with GANs, as I showed earlier. Nucleus, the core in the center there, combines all of the physics work that we do, defined materials that we actually create, path tracing, artificial intelligence techniques, and utilizes something called USD, which is born from Disney Pixar. For very high photorealistic capability. I don't unfortunately have the time to go into depth on Omniverse, but please contact me and I can send a lot more detail, and do test it out, because we have a ton of resources online, allowing you to actually go through and learn much more. There are over 80 free tutorials, for example. So again, a copy of these slides will be provided to everybody. But NVIDIA already has the platform to enable you, whether the compute is desktop, from a data center, or it's cloud provided. So please let us help. We have something called the Emerging Chapters program. It's there to empower developer communities in emerging markets for the latest knowledge and skills. Anybody can join for access to hundreds of code libraries and other technical resources. We also have the Deep Learning Institute that offers hands-on, self-paced or instructor-led industry workshops across data science, across robotics and accelerated computing. So please go online and take a look at that. And we also host many hackathons throughout the year, alongside the work that we do with the Frontier Development Lab, which, as mentioned earlier, is specifically for space applications. We can help put together hackathons to teach you more about utilizing accelerated computing and GPUs. And for startups, we have our Inception program that actually provides technology expertise, go-to-market support, VC connections even, and a lot more to thousands of AI startups. And what I mean by AI is AI utilizing GPU. So if you're developing any kind of solution, please join the developer program, take our code, use it, and let us help you to do that. And you can learn a lot more about that. And there's a lot more information, not just from us, but also from people who use our platform at our GPU Tech Conference that's actually virtual next month. So I just want to leave you with this thought, that understanding our world requires a global perspective. And all of the data, of course, that entails. We live in a very complex environment, so broadening our field of view, both physically and virtually, makes sense. You know, seeing the bigger picture, but also the whole picture. So thank you very much. Thanks, David, and to you all for listening. So if you have any questions, we're here to answer them. I'm not quite sure how much time we actually have left, but I'll just stop sharing my screen here and look at the Q&A.
No, that was wonderful. Thank you very much, both Alison and David. That was fascinating. You clearly do a lot of work at NVIDIA already in this space. So, and I was pleased as well, actually, to see the work you're doing in the developing world, because I think one concern maybe people have is the cost it takes to get set up with these training these machine learning models and buying these GPUs. So that was good to see as well. We have a question in the chat. I'm not sure which of you would like to pick that up. I guess this might relate to the new ARM chip you mentioned, but they're asking about the data transfer between CPU and GPU for global storm resolving models, which obviously, as you both alluded to, produce a huge amount of data, and how progress in future work is working towards that, solving that bottleneck.
Okay, David, do you want to take that, or do you want me to?
I mean, I'll answer. I mean, basically, all I can say is what we already know, which is that NVIDIA recognized this problem, that the transfer between CPU and GPU was a bottleneck. And that's why we decided to build our own CPUs, the Grace CPU, and it's just getting started. I mean, they're just putting it into new supercomputers as we speak. So we'll get to do an entire new, we'll have a new process for being able to simulate these models that we couldn't do before. And of course, having built them, I'm sure they will continue to improve them as time goes on, and it'll get better and better and faster and more tightly coupled. So I expect it to be a wonderful resource for enabling scientists to answer these questions.
And will that, I mean, sorry, Alison, go on.
Yeah, I was just going to say, I'll add a link to the chat now for everybody. I've got to remember to click it to everybody. We've been developing what's called RDMA for many, many years now. So the full documentation is actually here to dramatically speed up and even bypass the CPU in most cases. But of course, it depends on the individual application, and it's essentially getting down to the actual CUDA level. So that's the programming language for the GPU itself. But we've written that code for you, if that makes sense. And you can actually harness that depending on the specific application. But again, as David said, having our own CPU is improving that even more so. And what I mean by improving is reducing the latency, reducing and raising the throughput of data traveling around. Because when you're talking about trillions of floating point operations, obviously you have to have that as quick as possible.
I guess that also helps efficiency, which you talked about as well.
It's the only way, yeah.
One of the difficulties or barriers, I guess, in climate science is the fact that most of our models are written in Fortran and are slightly, well, the architecture is slightly archaic in that respect. And is that something that you're helping with? Are there libraries that you're developing to make that easier, that interface between Fortran and the GPU?
Yes, actually,
David has a wry smile.
this is the question I get most often. I think people who don't work in this area would be shocked to learn that about 90% of the codes are written in Fortran, with some C++ sprinkled in there for fun. And people are exploring lots of other ways of generalizing that, domain-specific languages and things like that. But it's still mostly Fortran. So if you want to train an AI model and get it to work with your Fortran code, there's a big barrier there because they live in very different worlds. And a number of people have tried to bridge this gap, and there's a number of solutions out there, mostly custom homegrown solutions. We are, in fact, working on this at NVIDIA. We have at least one, maybe two projects where we are, I don't want to commit to anything, but we're attempting to build our own bridges between Fortran and these training frameworks, these AI frameworks. So I can't promise when this kind of thing will be available, but we are very aware of this challenge, and it is something we are trying to address.
Fantastic.
And you can actually see some of that work on the link that I've put in there. Again, we hold many hackathons that actually walk folks through the process of using things like OpenACC, but also the latest high performance computing software development kit that we actually have that tries to address this. And as David said, it's focused mostly on Fortran because 90% in this arena anyway. But it's not that it can't be solved, because we're actually working on it now. It's just a case of working through each of those applications.
I have a slightly more general question to Alison, maybe, and you nicely outlined already sort of the role of industry in climate science, and yet primarily from the tech side. But I wonder also from your experience how we could really further deepen the relationship between industry and big data and tech sector and climate science. We're sort of running out of time. We really need to make urgent progress in many of these areas. Aside of things that exist already like FTL and so on, how could we deepen this relationship, and how could we work together to advance this a bit faster than we currently do? Do you have any thoughts on that?
So I would personally, if it's space related, and what I mean by that is satellite related, then please let us know and we can try to address this. But FTL it scales to about 10 challenges at the moment, but we could double that if we had more industry support. So this is basically researchers that are giving their time and energy over the summer period. So we could double the challenges that we're tackling on a yearly basis with more industry support. Alternatively, we actually have an internal program as well as our hardware grant program. Let me just put the link in the chat, that if you're working with a commercial partner, and that could be someone like ECMWF or the Met Office, for example. If you're developing AI code that is providing a solution and getting deployed, so we're committed to acting, not just developing research that could in the future. If you're working with commercial partners, we will provide funding, we will provide hardware. Simply apply via that link that I've sent, and we'd be more than happy to walk you through the actual process. And again, I think hackathons are a really good way. So that's kind of a shortened version of FTL. FTL is much more specific in that it's an actual challenge that we're going to address and get what's called a tech-ready level prototype at the end of that 8 weeks. Whereas with hackathons, they can be slightly more generic. It could be a much broader solution, but again, it's teaching people how to do that, and possibly people who aren't that familiar with using GPUs. Great,
thanks.
We have a more technical question from Alison Douglas in the chat. She wants to know if there's any work being done using graph neural networks to better incorporate multiple different types and forms of observations. I imagine she's envisaging satellite data. You mentioned that big stream of data. Is that something that you're looking to use at all?
I think we probably would. David may know better than me for the actual climate folks, but it's definitely something that was tackled in this summer FDL, and code will be released very shortly, if not the papers already, because we spend a lot of time developing after the summer to get papers submitted to places like NeurIPS, the world's biggest AI conference, for example. But there's no reason it couldn't be. And there've been actually developments, almost weekly on harnessing the most, state-of-the-art algorithms, and GNNs are definitely one of those. David, I don't know if you can speak on more climate focused.
Yeah, so we're working with ECMWF, which is, basically they do weather predictions, but, it's related to climate in that we want to be able to predict extreme weather under climate change. And yes, we're working with these guys on AI methods for improving data assimilation. And graph neural networks are one of many techniques that we have explored and are exploring. We have some pretty interesting projects ongoing with them right now, which are actually, one of them is just getting started in this area. So I would say yes, the answer is definitely we're exploring graph neural networks for this. This may or may not be the best way to do it, but there's a lot of great techniques out there and they come out so fast. It's a little bit hard to keep track of them all.
Yeah,
DeepMind as well just published a really interesting paper as well. So there's lots happening, especially in the climate arena. Yeah,
indeed. I was just going to say that's a good point to wrap up. There's a slightly provocative question in the chat which I quite like, but maybe
go ahead. I don't mind those.
Okay, go on. If we keep it a relatively short answer, it's something we could spend a little while on. But so the question is, you obviously have these super realistic virtual worlds that you can create, these synthetic worlds. What if people who with maybe slightly dubious ethical motives wanted to use them to spread fake news, conspiracy theories, etc.? And I guess this touches on the world of deep fakes and so forth. Is that something you
to be honest, that's no worse than using the common ones like Facebook and Twitter. And there's actually a lot being done by the social media groups. But I remember when I was actually, I was a mature student going back to university to study artificial intelligence. And, I can remember that we had this discussion about the use of virtual worlds, which was a little bit strange for me because I've been in something called Second Life, which is an entire virtual world, where you literally build houses and create, cultures, for example. But I've been in Second Life because my virtual charity operates from there. We don't have an office anywhere physically in the world, but we have an office in Second Life where people can actually come and visit and see what we do. And, on the ground on Earth, we actually deal with volunteering. In East Africa, in Brazil, for example, anything for sustainable development. So it's always bizarre that you kind of that there's those dark areas, just as we have the dark web. But actually, there is a lot of good that these worlds can do in connecting people, in allowing people to learn more, and for free, actually. But equally, it's the only way that we will get successful AI now, because of the fact that working in those virtual arenas, as well as I said, it's cost-free, it's risk-free, but it's creating the data that we need to make robust artificial intelligence systems. And what I mean by robust is reducing the bias and covering, scenarios, as I said earlier, that we couldn't cover in the real world. You can't drive a car with an entire family into a wall just to see what happens, but there are games out there that do that. People, GTA is a big part of AI right now. We use it a lot for research.
Absolutely. No, and I think there are certainly positives. I mean, you can easily imagine these virtual worlds being used as a communications tool to show how your town or village will change under different climate scenarios.
Yeah.
Brilliant. I think we'll have to leave it there, but thank you very much for the talks and the interesting discussion. The video will be up for those of you who maybe missed the start, or also on YouTube after this. But if you have any other questions, I'm sure Alison or David will be happy for you to contact them. So thank you very much, and I'll hand over to Bastian to close us out.
Thank you.
Thank you, Duncan. And thank you everyone for joining today. We have several other sessions and we're posting the links in chat. So please join us soon. And we'd like to thank once again everybody, our speakers, Alison, David, our hosts, Philip and Duncan, and I hope to see you soon.
Thank you.
Thank you.
Rewind selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector.